November 14, 1942. Bath, Maine. The keel-laying ceremony at Bath Ironworks should have been routine, another warship beginning its journey from blueprint to battle. But the vessel taking shape that morning represented something unprecedented in naval architecture. A ship designed to deliberately run aground, a contradiction so profound that it challenged everything naval engineers had learned about designing vessels that were meant to stay afloat. The landing ship, tank soon to be known simply as the LST, would become one of World War II's most important vessels, not because it carried the heaviest guns or the thickest armor, not because it moved faster or hit harder than anything else afloat. The LST mattered because it solved an impossible problem: how to deliver 30 Sherman tanks directly onto a hostile beach, discharge them in minutes rather than hours, and then return to sea under its own power. Before the LST, amphibious assaults required complex operations involving multiple ship types, elaborate logistics, and enormous time. After the LST, armies could cross oceans and attack defended coastlines with an efficiency that changed warfare itself. The story begins not with ships, but with disaster. June 4, 1940, Dunkirk. British forces trapped against the French coast executed a desperate evacuation. 338,000 soldiers escaped, but they left behind virtually everything else: 7,000 tons of ammunition, 20,000 motorcycles, 6,500 vehicles, 445 tanks, all of Britain's heavy equipment abandoned on French beaches because there was no way to evacuate it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The loss of equipment was catastrophic. Britain's army had been saved, but it was now an army without tanks, without vehicles, without the mechanized capability modern warfare demanded. Worse, the Dunkirk experience revealed a fundamental problem. Moving armies across water was vastly easier than moving their equipment. Ships could carry soldiers, but tanks, artillery, vehicles, those required specialized equipment that the British simply didn't have. Winston Churchill understood immediately. Britain would eventually need to return to continental Europe. When that day came, British forces would need to bring overwhelming mechanized power. They couldn't rely on capturing ports; the Germans would destroy them before retreating. They couldn't depend on building temporary harbors in calm conditions. Warfare didn't allow that luxury. They needed a way to deliver tanks directly onto beaches in any conditions, defended or not. Churchill issued a characteristically direct order to his military planners in late 1940. Design and build ships that can deliver tanks directly to beaches, not complicated barges that required specialized handling, not ships that anchored offshore and slowly unloaded, ships that could cross oceans, approach hostile shores, and discharge their cargo directly onto sand, ships that naval engineers would say couldn't exist. The British Admiralty turned to their naval architects with Churchill's impossible requirement. The architects responded with what would politely be called extreme skepticism. For centuries, naval design had been governed by one fundamental principle: ships must float. Their hulls were shaped to move through water efficiently. Their draft, how deep they sat in the water, was carefully calculated. Running a ship onto a beach intentionally was called grounding. It was something that happened by accident, something that often destroyed ships. Churchill wanted ships designed to ground themselves deliberately, discharge cargo, and then refloat and return to sea. The naval architects explained patiently why this was impossible. A ship designed to operate in deep water would have too deep a draft to approach beaches. A shallow draft ship that could reach beaches wouldn't be seaworthy in open ocean. A ship with a bow designed to beach would be dangerously unstable in rough seas. And even if you somehow solved all these problems, how would tanks get off the ship? They couldn't jump. They couldn't be craned over the side onto beaches. They needed to drive off under their own power, which required ramps, which created their own engineering nightmares. The British persisted. If naval architects said it was impossible, then naval architects would have to become innovative. Throughout 1941, British designers worked on concepts. They examined existing ships, looking for any that combined ocean-going capability with shallow draft. They studied landing craft from World War I, small boats that could approach beaches but couldn't cross oceans. They consulted with tank officers about what would be needed to get armored vehicles off ships and into combat quickly. The breakthrough came from thinking about the problem differently. Instead of asking how to make an ocean-going ship that could reach beaches, they asked, what would a ship look like if it was designed from the start to beach itself? This reframing changed everything. Start with the beach landing as the primary requirement, then work backward to make the vessel seaworthy enough to reach the beach. This produced a radical design. The ship would have a flat bottom instead of the curved hull that traditional ships used. This flat bottom would let it sit stably on beaches. The bow would be blunt and square rather than streamlined. This allowed a large ramp to be built into the front. The ship would be very long relative to its width, giving it directional stability even with that flat bottom. And crucially, ballast tanks would allow the ship to adjust its draft, riding high in the water when approaching beaches and trimming down when ready to offload. By mid-1941, British designers had produced what they called the Atlantic Tank Landing Craft. It could carry tanks. It had enough range to cross the English Channel. It incorporated a bow ramp. But it was too small. It could carry perhaps 3 tanks, maybe 18 fully equipped soldiers. For the invasions Churchill envisioned, Britain would need hundreds of these vessels, and they would need to be much larger to make the tremendous construction effort worthwhile. The British turned to America. In early 1942, even before the United States formally entered the war, British representatives approached American shipbuilders with their design concepts. They needed American industrial capacity, they needed American engineering expertise, and they needed someone who could scale up the concept to create truly useful vessels. The Americans examined the British designs with interest and considerable skepticism. American naval architects had the same fundamental concerns the British had already overcome. Ships aren't supposed to run aground, but the Americans had something the British didn't: experience with inland waterways. The United States had extensive river systems. American shipyards built river barges and shallow draft vessels routinely. The flat-bottom design that seemed radical to ocean-focused British designers was familiar to American engineers who'd built Mississippi River vessels for decades. The U.S. Navy's Bureau of Ships took on the project. They assigned it to a team led by naval constructor John Niedermayer. Niedermayer looked at the British concept and saw potential. But he also saw that the British were still thinking too small. If America was going to build these vessels, they should be big enough to matter, big enough to carry meaningful loads, big enough to justify the enormous resources that would be required. Niedermayer's team started with requirements. The vessel needed to carry at least 20 Sherman tanks or equivalent cargo. It needed to cross the Atlantic under its own power. It needed to operate in both calm and moderate seas. It needed to beach itself on gradients ranging from 1 in 50 to 1 in 100, the typical range for invasion beaches. It needed to discharge its cargo rapidly, then retract from the beach and return to service. From these requirements came a design unlike anything in naval history. The LST would measure 328 feet in length and 50 feet in beam width. It would displace 4,000 tons when fully loaded. The flat bottom would run the ship's entire length. The bow would be completely square, housing massive clamshell doors that opened to reveal a ramp. The stern would be blunt, housing the engine room and crew quarters. Inside, the LST would be essentially a floating parking garage. The main deck, the tank deck, would run nearly the entire length of the ship, uninterrupted by bulkheads or obstacles. This gave roughly 100 feet of clear space where vehicles could be parked in rows. Above the tank deck, a weather deck provided additional space for vehicles, supplies, and anti-aircraft guns. The propulsion system reflected the unusual requirements. The LST needed to be ocean-going but also needed very shallow draft when approaching beaches. The solution was twin diesel engines driving separate shafts. Each engine produced 1,700 horsepower. This gave enough power to push the heavy, flat-bottomed hull through ocean swells at about 11 knots maximum speed. Not fast, but adequate. The engines were positioned well aft and as high as possible. The propeller shafts were angled to keep the propellers from extending too far below the hull. When the ship was in landing configuration with bow trimmed down and stern trimmed up, the propellers remained in deep enough water to function. This was critical. The ship needed propulsion to retract from the beach after unloading. The ballast system was sophisticated. Large tanks throughout the hull could be filled or emptied to adjust the ship's trim. When approaching a beach, pumps emptied the forward ballast tanks and filled the aft tanks. This raised the bow and lowered the stern, reducing forward draft to as little as 3 feet. The ship could reach very close to shore. After unloading, the process reversed. Forward ballast tanks filled, aft tanks emptied. The bow settled back down and the stern came up. The ship's weight now distributed differently. It could use its engines to back away from the beach. In moderate conditions, a beached LST could retract itself within an hour of completing discharge. The bow doors and ramp system represented extraordinary engineering. The bow featured two massive doors hinged at the sides. Each door weighed several tons. When closed, they formed the ship's bow, sealed against seawater. When opened, they swung outward like clamshell halves, revealing the interior tank deck. Behind the doors, a ramp section could be lowered. This ramp was essentially a section of the tank deck that pivoted downward on massive hinges. When lowered, it bridged from the ship's interior to the beach surface. Tanks could drive directly from the ship onto sand. The engineering challenge was making this work reliably. Salt water, sand, and constant stress from waves would destroy any system that wasn't robustly designed. The doors and ramp used massive hinges and hydraulic systems. Everything was sized far beyond theoretical requirements because the designers knew that combat conditions would test every component to failure. Mock-ups were built and tested repeatedly. Engineers discovered problems and solved them. The door seals leaked initially, so they were redesigned. The ramp hinges jammed with sand, so they were modified. The hydraulic systems failed in cold water, so different fluid was specified. By mid-1942, the design was finalized. Now came the greater challenge, building them in sufficient numbers. The United States would eventually build over 1,000 LSTs. This required enormous industrial mobilization. Shipyards across the country received contracts. Some were traditional shipyards familiar with naval construction. Others were facilities that had never built ships before but had heavy steel fabrication experience. Bridge builders, steel mill operators, anyone with welding capability and large covered spaces. The LST design was deliberately simplified to enable this distributed production. The hull used large prefabricated sections that could be welded together. Unlike traditional ships with compound curves and complex geometry, the LST's flat sides and rectangular construction lent itself to simple fabrication. Sections could be built inland at steel mills, transported by rail to shipyards, and welded into complete hulls. This modular construction approach was revolutionary. Traditional shipbuilding required skilled craftsmen who understood the complex geometry of curved hulls. LST construction required welders who could join flat sections. The skill requirements were lower, which meant more facilities could participate and more workers could be trained quickly. Production began in earnest in late 1942. The first LSTs were commissioned in early 1943. Initially, construction took several months per ship, but as yards gained experience and refined their processes, construction time dropped dramatically. By mid-1943, efficient yards were launching LSTs in 6 to 8 weeks. The crews who would operate these strange vessels required training that didn't exist in naval tradition. LST commanders needed to understand both blue water seamanship and beach landing techniques. They needed to navigate open ocean but also judge tides, beach gradients, and surf conditions. They needed to work with Army officers who controlled the cargo, but naval officers who controlled the ship. Training centers were established where LST crews practiced beach landings repeatedly. They learned to read beaches, identifying suitable landing points. They learned to trim the ship properly for beaching. They learned the complex ballet of opening bow doors, lowering ramps, and directing vehicles off the ship while maintaining stability. And they learned emergency procedures for the inevitable times when things went wrong. The first combat test of the LST concept came in July 1943 during Operation Husky, the invasion of Sicily. 157 LSTs participated, carrying British and American forces across the Mediterranean. The operation would prove whether these ungainly vessels could actually perform under combat conditions. The LSTs approached Sicilian beaches in the pre-dawn darkness of July 10th. German and Italian forces held defensive positions overlooking the invasion beaches. Artillery was registered on likely landing points. Machine gun nests covered the waterline. The defenders expected landing craft, but nothing on the scale of what was approaching. The first LSTs grounded themselves on schedule. Bow doors opened, ramps lowered, and Sherman tanks rolled directly onto Sicilian sand, engines roaring, still dry and fully operational. The speed was shocking. Traditional landing operations required ships to anchor offshore, lower landing craft, transfer vehicles to landing craft, run the landing craft to shore, unload vehicles in surf, and repeat endlessly. This process took hours for each ship. An LST could beach itself, discharge 20 tanks in 10 minutes, and retract. The time compression was revolutionary. German commanders watching the landings saw continuous streams of armor pouring onto beaches. Intelligence reports went up the chain describing impossible landing rates. The reports were accurate. The impossible was happening because American engineering had made it routine. Not everything went perfectly. Several LSTs grounded on underwater obstacles. Others misjudged beach gradients and couldn't fully lower their ramps. A few took artillery hits while approaching shore, but the overwhelming majority completed their missions successfully. And even damaged LSTs often managed to discharge most of their cargo before withdrawing. The Sicilian operation validated the LST concept completely. Naval officers who'd been skeptical became converts. Army officers who'd worried about getting tanks ashore safely found their concerns eliminated. The LST wasn't elegant and it certainly wasn't fast, but it worked. It worked reliably, and it worked at a scale that changed amphibious warfare fundamentally. After Sicily came Italy. The Salerno landings in September 1943 employed even more LSTs. Then Anzio in January 1944. Each operation refined tactics and procedures. Crews learned optimal approach angles. Beachmasters officers who controlled landing operations from shore learned to direct LST traffic efficiently. The ships themselves proved remarkably durable, surviving groundings and combat damage that would have sunk traditional vessels. The LST's flat bottom, while creating terrible handling in rough seas, actually made the ships more resilient to mine and torpedo damage. A traditional V-shaped hull concentrated underwater explosions into the keel, often breaking the ship's back. The LST's flat bottom distributed explosive force across a larger area. Ships that took mine hits often survived with localized damage rather than catastrophic failure. This durability mattered enormously. In sustained operations, LSTs would beach themselves repeatedly, often several times per day. They operated in shallow water where mines were common. They worked close to shore where they were vulnerable to artillery. Any vessel less robust would have been lost quickly. The LST absorbed punishment and kept functioning. By early 1944, Allied planners were preparing for Operation Overlord, the invasion of Normandy. This would be the largest amphibious operation in history. Everything depended on getting overwhelming force onto French beaches quickly. And that meant LSTs. Hundreds of them. The planning for Normandy revealed just how thoroughly the LST had transformed amphibious warfare doctrine. Earlier plans for invading France had assumed operations would need to capture a major port quickly. Without port facilities, the thinking went, forces couldn't be sustained. The invasion would fail if a port wasn't captured within days. The LST changed this calculation completely. With enough LSTs, forces could be supplied directly over beaches indefinitely. Ports were still valuable, but they weren't immediately critical. This strategic flexibility was profound. It meant planners could choose invasion sites based on tactical considerations rather than port proximity. It meant German defenders couldn't concentrate forces at a few predictable port cities. Operation Overlord employed more than 200 LSTs. They were organized into convoys and dispatch groups, carrying British, American, and Canadian forces. The ships loaded at ports throughout southern England during May 1944. Sherman tanks drove aboard. Artillery pieces were secured on tank decks. Trucks, jeeps, ammunition, fuel, medical supplies, everything an army needed was loaded onto these flat-bottomed vessels. The crossing of the English Channel on June 5th and 6th was harrowing. Weather conditions were marginal. Supreme Commander Eisenhower had delayed the invasion 24 hours, hoping for improvement. When he finally ordered the operation to proceed, conditions were still far from ideal. Rough seas and high winds created miserable conditions for the unwieldy LSTs. Crews struggled to maintain formation. The flat bottoms made LSTs notoriously poor in rough water. They rolled viciously in swells. They were slow, making them difficult to maneuver in formation. Many crew members and embarked soldiers suffered terrible seasickness during the crossing. But the ships kept going. They had to. Everything depended on them reaching the beaches. Dawn on June 6, 1944. 5 beach sectors stretched across 50 miles of Norman coast. Utah, Omaha, Gold, Juneau, Sword. At each beach, LSTs waited offshore for H-hour, the moment when the assault waves would land. The initial assault went in on a smaller landing craft. infantry to secure the beaches, combat engineers to clear obstacles. Then, once beaches were secured enough, the LSTs would come in. At Utah Beach, LSTs began landing shortly after H-hour. The beach had been secured quickly with relatively light casualties. LSTs drove straight up to the waterline, discharged their tanks and vehicles, and backed away. The efficiency was remarkable. Within hours, hundreds of vehicles were ashore and moving inland. Omaha Beach told a different story. German defenses there were far stronger than intelligence had predicted. The initial assault waves suffered terrible casualties. Bodies and destroyed equipment littered the beach. For hours, the landing was in doubt. LSTs waited offshore, watching the carnage, their crews knowing that if they went in under current conditions they'd be destroyed. By afternoon, American forces had finally secured portions of Omaha Beach. The decision was made to bring LSTs in despite continued German fire. The ships had to land. The forces ashore desperately needed the tanks and supplies those LSTs carried. The alternative was abandoning the beach entirely. LSTs approached through artillery fire. Several took hits. One, LST 507, was struck by German artillery while approaching shore. The hit penetrated the hull and ignited fuel stored in the tank deck. Fire spread rapidly through the ship. The crew abandoned the vessel. LST 507 burned and sank in shallow water, a total loss. But other LSTs kept coming. They beached themselves under fire. Bow doors opened despite German machine guns raking the beach. Ramps lowered, and tanks rolled off directly into combat. Sherman crews who'd spent the voyage seasick and frightened found themselves in battle within minutes of landing. But they were ashore, they were operational, and they turned the tide at Omaha Beach. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Normandy landings consumed massive numbers of LSTs. Ships made multiple trips back to England to reload and return. They operated around the clock in all weather. Crews went days without real sleep, snatching rest in shifts between landing operations. The pace was exhausting and dangerous, but it worked. Within a week of D-Day, over 326,000 men, 54,000 vehicles, and 104,000 tons of supplies had crossed the English Channel. Much of this material came ashore directly from LSTs. The artificial Mulberry harbors that were constructed helped, but even before those were operational, LSTs were sustaining the invasion force. The LST's ability to deliver cargo directly to beaches became even more critical when a severe storm on June 19th destroyed much of the American Mulberry Harbor. Planners had feared this would be catastrophic. With the harbor gone, how could supplies reach the forces now fighting inland? The answer was LSTs. They continued landing through the storm and its aftermath, maintaining supply flow when nothing else could. This operational flexibility was the LST's greatest strategic contribution. It made Allied forces independent of port facilities. It allowed sustained operations in conditions that would have stopped earlier amphibious campaigns. It gave commanders options that simply hadn't existed before. The ugly, slow, uncomfortable LST had become indispensable. The Pacific Theater created even greater demands on LST capabilities. Island-hopping campaigns required landing forces on hostile beaches, separated by thousands of miles of ocean. Traditional amphibious doctrine would have made this strategy impossible. LSTs made it routine. In the Pacific, LSTs operated at the extreme limit of their capabilities. Crossing from Australia to New Guinea stretched their range. Operating in tropical conditions tested their crews. Coral reefs created navigation hazards that Mediterranean and European crews never faced, and Japanese defenders fought with a ferocity that created appalling casualties. But the LSTs kept landing. Tarawa in November 1943, the Marshalls in early 1944, the Marianas that summer. Each operation put more demand on these vessels, and each operation proved again that the basic concept was sound. Direct delivery of heavy equipment to hostile beaches was not only possible but could be done reliably at scale. The Philippines campaign from October 1944 through July 1945 employed LSTs more extensively than any previous operation. General MacArthur's return to the Philippines required landing forces on multiple islands across an archipelago. Traditional logistics would have been impossible. LSTs made it achievable. At Leyte Gulf in October 1944, LSTs delivered the tanks and artillery that American forces needed to push inland from the beaches. At Luzon in January 1945, they sustained a major offensive against dug-in Japanese defenders. And throughout the campaign, they moved supplies between islands, functioning as versatile transport vessels that happened to be capable of beaching themselves. The culmination of Pacific LST operations came with the planning for Operation Downfall, the proposed invasion of Japan. Planners estimated this operation would require over 1,000 LSTs operating simultaneously. The scale was unprecedented, but by mid-1945, many LSTs existed. Production had continued throughout the war. Shipyards across America had delivered vessel after vessel. The industrial capacity that had seemed impossible in 1940 had become routine by 1945. Operation Downfall never occurred. Japan's surrender in August 1945 ended the war. But the fact that such an operation was even conceivable showed how thoroughly the LST had transformed amphibious warfare. An invasion of the Japanese home islands using 1940 technology would have been suicidal. With LSTs, it became theoretically feasible, though it still would have been horrifically costly. The human experience of serving on LSTs rarely made headlines but was remarkable in its own way. These ships were uncomfortable. The flat bottom created terrible motion in rough seas. Crew quarters were cramped. In tropical climates, interior spaces became unbearably hot. The constant beaching operations meant crews were always working, always under stress. Yet LST sailors developed fierce pride in their vessels. They knew the ships were ugly. They joked about the acronym standing for Large, Slow Target. But they also knew their ship could go places and do things that no other vessel could match. An LST could cross an ocean, survive combat, beach itself in the surf, discharge 20 tanks, and do it all again the next day. That capability bred respect. The tank crews and soldiers who rode LSTs had their own complicated relationship with these vessels. The voyage was usually miserable. Seasickness was almost universal among embarked troops during rough crossings. The combination of diesel fumes, motion, and crowded conditions made LSTs floating misery for passengers. But when those bow doors opened and the ramp lowered onto a hostile beach, every soldier was grateful for the LST. They drove or walked directly from the ship onto land. They weren't soaked from landing craft. They weren't scattered across miles of beach. They arrived as formed, units with their equipment intact and ready to fight. That was worth any amount of voyage discomfort. The statistics told the story of LST contribution to Allied victory. Over 1,000 LSTs were built during the war. They participated in every major amphibious operation from Sicily through Okinawa. They carried millions of tons of cargo. They transported hundreds of thousands of vehicles, and they did it with relatively modest losses. Approximately 24 LSTs were sunk by enemy action during the war. Another dozen or so were lost to accidents, weather, and other non-combat causes. For vessels that routinely operated in the most dangerous possible conditions, shallow water near hostile shores, this loss rate was remarkably low. The LST's robust design and operational flexibility kept them surviving when more conventional vessels would have been destroyed. The end of World War II didn't end the LST's service. Many remained in U.S. Navy service through the Korean War. They landed Marines at Incheon in September 1950, repeating their World War II role in a new conflict. Others were transferred to Allied navies. Britain, France, Greece, Taiwan, and numerous other nations operated LSTs for decades after the war ended. Some LSTs found civilian careers. Their ability to carry heavy cargo and beach themselves made them valuable for remote cargo operations where ports didn't exist. In the Pacific, LSTs transported supplies to islands without harbor facilities. In South America, they served rivers too shallow for conventional ships. The basic design proved so versatile that variations continue operating today. The U.S. Navy eventually replaced LSTs with more sophisticated amphibious vessels. The LST was succeeded by the Newport-class tank landing ships in the 1960s and 70s, which used different designs. Modern amphibious vessels use different concepts entirely, including well decks where landing craft are loaded inside the ship, and air cushion landing craft that ride over water on cushions of air. But these modern vessels are descendants of the LST concept. They exist because the LST proved that heavy equipment could be delivered directly to beaches, and that specialized vessels designed for this purpose could operate effectively at scale. The LST established the doctrinal foundation that modern amphibious warfare still uses. The engineering legacy of the LST extended far beyond the vessels themselves. The design process forced naval architects to question fundamental assumptions about what ships could and should do. For centuries, ships had been designed to stay afloat in deep water. The LST proved that vessels could be designed to operate in multiple environments: deep water for transit, shallow water for approach, and solid ground for cargo operations. This multi-environment design philosophy influenced post-war engineering across multiple domains. The concept that a single vehicle could be optimized for multiple contradictory requirements appeared in other military systems: amphibious vehicles that operated on land and water, aircraft that performed multiple mission types. The LST demonstrated that accepting compromises in some areas could create revolutionary capabilities in others. The LST was never going to win races. Its flat bottom and blunt bow made it slow and uncomfortable in any sea state. But speed wasn't the requirement. The requirement was delivering tanks to beaches, and for that mission, the LST was optimized perfectly. This focus on mission-specific optimization, rather than general excellence, became a guiding principle in post-war military procurement. The construction methods developed for LST production also had lasting impact. The modular assembly techniques, the use of prefabricated sections, and the distribution of production across multiple non-traditional shipyards all became standard practice. When the United States needed to rapidly expand its merchant marine during the Cold War, the techniques developed for LST construction provided the template. The Liberty ships that sustained Allied supply lines during World War II used similar mass production techniques. But Liberty ships were merchant vessels built to existing maritime design traditions, just produced faster. LSTs represented something more radical, a completely new type of vessel built using industrial methods that traditional shipbuilding had never employed. The LST proved that ships could be manufactured like automobiles if the design was appropriate. Individual vessels had their own stories. LST-325, commissioned in February 1943, participated in the Sicily invasion, then Salerno, then Normandy. After the war, it was transferred to the Greek Navy, where it served until decommissioned in 1999. A group of American LST veterans purchased the ship and sailed it across the Atlantic to the United States in 2001. Today, LST-325 operates as a museum ship in Evansville, Indiana, maintained by volunteers, many of them veterans who served on LSTs. Walking through LST-325 today provides visceral understanding of what these vessels were. The tank deck is vast and empty, echoing with footsteps. It's easy to imagine 20 Sherman tanks parked in rows, crews performing last-minute maintenance before landing. The bow doors, now permanently closed, still show their massive hinges and the complex mechanisms that opened them under combat conditions. The crew spaces are cramped. Bunks are stacked 3 high in compartments, barely large enough to turn around in. The galley that fed hundreds of men is tiny by modern standards. Everything about the ship speaks to functionality over comfort. This was a working vessel built to accomplish a specific mission. Every design choice sacrificed crew comfort for cargo capacity or operational capability. But standing on the tank deck, looking forward toward those bow doors, the revolutionary nature of the design becomes clear. This space connected directly to beaches. Tanks didn't need to be hoisted over the side by crane or transferred to smaller craft. They drove straight from this deck onto hostile shores. That direct connection was the LST's genius, eliminating transfer steps that consumed time and created vulnerability. The statistics of what LSTs accomplished during World War II remain staggering when examined closely. In the European theater alone, LSTs made over 40,000 individual beaching operations. 40,000 times, these vessels approached hostile or potentially hostile shores, grounded themselves, discharged cargo, and retracted. Each operation risked the ship and crew. Each operation kept Allied forces supplied and mobile. In the Pacific, the numbers were smaller, but the distances were greater. LSTs crossed thousands of miles of ocean to reach remote islands. They operated without the shore facilities that European operations could draw on. They sustained campaigns across an area covering millions of square miles of ocean. The logistical achievement was extraordinary. The cargo delivered by LSTs included more than just tanks. Medical supplies, ammunition, food, fuel, construction equipment, and countless other necessities all came ashore from LST tank decks. In sustained operations like the Philippines campaign or the final advance across Germany, LSTs functioned as the logistical backbone of entire armies. Traditional supply chains relied on ports and warehouses. LST-based logistics delivered supplies directly from ships to fighting forces. This logistical flexibility gave Allied commanders strategic options that Axis forces couldn't counter. German and Japanese defensive plans assumed that invading forces would be constrained by port capacity and vulnerable supply lines. LSTs made these assumptions obsolete. Allied forces could land anywhere, could be sustained over open beaches, and could maintain operational tempo independent of captured infrastructure. The psychological impact on defenders was significant. German troops in Normandy and Italy quickly learned that Allied forces could appear anywhere. The coast wasn't defensible because the Allies didn't need ports. They could simply drive their tanks directly onto any beach they chose. This reality forced dispersion of defensive forces and prevented concentration of strength. Every beach became a potential invasion site that required at least minimal defense. Japanese forces in the Pacific faced the same dilemma. Island garrisons couldn't concentrate at ports because American forces would simply land elsewhere. The LST gave Allied forces the initiative. They could choose when and where to attack. Defenders had to prepare everywhere, spreading their already inadequate forces even thinner. The engineering challenges that LST designers overcame went beyond the obvious problems of creating a beachable hull. The propulsion system required careful design to function when the ship's stern was trimmed high during beach operations. The ballast system had to work reliably in combat conditions with damaged pumps or ruptured tanks. The bow door mechanisms needed to function after ships had been repeatedly grounded on sand, coral, and rock. These systems evolved throughout the war. Early LSTs had problems with bow door seals that leaked. Later versions improved the sealing systems. Early LST ramps sometimes jammed when contaminated with sand. Modifications added flushing systems to clear debris. The ships got better through continuous refinement based on operational experience. This iterative improvement process was characteristic of American wartime engineering. Unlike German forces that often sought perfect solutions before production, American engineers accepted good enough solutions and improved them through use. The LST was never a perfect vessel. It was an adequate vessel that became progressively more capable through hundreds of small, buoyant improvements implemented across the fleet. The crew training programs also evolved. Initial LST crews often had minimal amphibious training. They learned by doing, sometimes disastrously. By mid-war, structured training programs walked crews through beach landing procedures in controlled conditions before they faced combat. Specialized schools taught navigation techniques for shallow water operations. Mock-up ships allowed practice with bow door and ramp systems. This professionalization of amphibious operations created a capability that persisted after the war ended. The U.S. Navy and Marine Corps developed amphibious warfare doctrine based on LST capabilities. Training centers continued operating. Specialized equipment continued being developed. The institutional knowledge gained through thousands of LST operations became foundational to American military amphibious capability that continues today. The international impact of the LST was equally significant. British forces used LSTs extensively, though they often operated under American command due to production limitations. British LST crews developed their own techniques and traditions. French forces used LSTs in their operations in Indochina after World War II ended. The vessels became a common element of naval forces worldwide. The Soviet Union received LSTs under Lend-Lease, but used them differently than Western allies. Soviet doctrine favored smaller landing craft for tactical operations. But even the Soviets recognized the LST's value for logistical support. Soviet LSTs sustained operations in the Black Sea and supported the Manchurian campaign in 1945. This widespread adoption proved the LST concept's universality. The design wasn't just suitable for American industrial methods or Allied operational doctrine. It was a fundamentally sound solution to the problem of amphibious logistics that any military force could adopt and benefit from. The cost-effectiveness of LSTs deserves examination. Each vessel cost approximately $1.5 million to construct, during the war expensive but not extravagant by wartime standards. A single LST could carry cargo equivalent to multiple Liberty ships' worth of equipment directly to a beach in a single trip. The operational efficiency was remarkable. Compare this to alternative methods. Traditional amphibious operations required transport ships, cargo vessels, landing craft, port facilities, and elaborate logistics chains. An LST eliminated most of these intermediaries. It could load at a port, cross an ocean, and discharge directly onto a beach. The reduction in required shipping and handling infrastructure represented enormous savings in resources and time. The total tonnage delivered by LSTs during World War II exceeded 100 million tons. This figure includes multiple trips by the same ships, but represents actual cargo moved from origin to beach. Traditional shipping methods would have required many more vessels and much longer time to move equivalent cargo. The LST's efficiency was a force multiplier that enhanced Allied logistics beyond its nominal cargo capacity. The human cost of LST operations was mercifully low compared to other aspects of amphibious warfare. Approximately 1,500 American sailors died serving on LSTs during World War II, about 1.5 crew members per vessel over the entire war. This was far lower than the casualty rates for infantry, aircrew, or submarine sailors. The relatively low casualties reflected both the LST's durability and the doctrine that governed its use. LSTs didn't go into beach landing operations until initial assault waves had secured at least minimal control. They operated with air superiority protecting them, and their robust construction meant they survived damage that sank more fragile vessels. The ships protected their crews reasonably well, given the hazardous nature of their missions. For the soldiers and Marines who rode LSTs into combat, the experience was universally memorable. Most recalled the voyage as miserable, the seasickness, the cramped conditions, the diesel fumes, but they also remembered the moment when bow doors opened and they saw the beach ahead. That moment of transition from helpless passenger to active combatant stayed with veterans for decades. Tank crews particularly appreciated LSTs. A Sherman tank sealed for water operations could theoretically be landed from conventional landing craft, but it was risky and often resulted in drowned tanks when waves swamped exhaust systems. LSTs delivered tanks completely dry and immediately operational. Tank commanders could start their engines while still inside the ship, warm up the systems, and drive off ready to fight. This operational readiness saved lives and won battles. The ultimate validation of the LST design came from the fact that the fundamental concept remains viable today. Modern amphibious vessels are larger, more sophisticated, and use different technologies, but they're still doing what LSTs did, delivering heavy equipment directly to shores without requiring port facilities. The mission hasn't changed. The LST proved the mission was achievable. When we examine technological breakthroughs that changed World War II's outcome, we tend to focus on dramatic innovations. Radar, proximity fuses, nuclear weapons. These were important, certainly. But the LST's contribution was arguably more significant. It didn't win battles directly. It made winning battles possible by ensuring that forces had the equipment and supplies they needed when they needed them. The LST represented a different kind of innovation, not a scientific breakthrough but an engineering insight. Naval architects looked at an impossible requirement and found a solution by questioning their assumptions. Ships had to stay afloat, except when they didn't. Ships couldn't have flat bottoms, except when flat bottoms were exactly what the mission required. Ships needed deep draft for seaworthiness, except when shallow draft was more important. This willingness to challenge conventional wisdom, to accept that different requirements produced different optimal solutions, was characteristically American. European naval traditions were ancient and conservative. American engineers, less constrained by tradition, were willing to try radical approaches if the mission demanded it. The LST embodied this pragmatic creativity. The vessels that served so effectively during World War II slowly disappeared in the decades after the war ended. Most were scrapped in the 1950s and 60s as the Navy modernized its amphibious fleet. A few served in foreign navies until the 1980s or 90s. Fewer than a handful survive today as museum ships. But the legacy persists in less visible ways. Every modern amphibious operation uses doctrine descended from LST operations. Every naval architect designing amphibious vessels draws on lessons learned from LST experience. And every military planner understands that shore-to-shore logistics, delivering cargo directly from ships to beaches, is a viable operational concept because LSTs proved it 7 decades ago. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe. The story of how engineers designed LSTs to beach themselves and deploy 20 tanks in minutes is ultimately a story about solving problems by refusing to accept that they can't be solved. Naval tradition said ships shouldn't run aground. Practical necessity said armies needed tanks delivered to beaches. Engineering ingenuity reconciled these contradictory requirements by designing vessels specifically for the mission rather than adapting existing designs. This mission-focused design philosophy produced an ungainly, uncomfortable, slow vessel that nobody would mistake for a thing of beauty. But it was perfectly optimized for what it needed to do. It could cross oceans, beach itself, discharge heavy cargo in minutes, and return to service. That capability changed amphibious warfare and helped win World War II. The young engineers who designed the LST, the shipyard workers who built over 1,000 of them, the sailors who operated them in combat, and the soldiers who rode them into battle created something that persists beyond the physical vessels. They proved that revolutionary capabilities could come from questioning assumptions and designing for specific missions rather than general excellence. When someone says it can't be done because it's never been done that way, the LST story provides the answer. Design it differently. Optimize for the mission. Accept compromises where they don't matter, to gain capabilities where they do, and build it in sufficient numbers that the concept proves itself through repeated success. That's what LSTs did. They were never supposed to exist according to traditional naval architecture. They existed anyway because the mission demanded them. They worked because engineers refused to accept that contradictory requirements couldn't be reconciled. And they changed warfare because sometimes the impossible just needs proper engineering. The LST wasn't the most powerful warship of World War II. It wasn't the fastest or the most heavily armed, but it might have been the most important. It delivered the armies that won the war. It sustained them across oceans and onto hostile shores, and it did it all while looking absolutely nothing like what anyone thought a ship should be. That's innovation. Not making existing things better, but making entirely new things that solve problems in ways nobody had imagined before. The LST solved the problem of amphibious logistics by becoming a ship that deliberately ran aground. The contradiction became the solution. And thousands of these flat-bottomed, slow, ugly vessels helped save the world.